ora everyone. Thank you for tuning into our lunchtime webinar today with RTSA. We'll just give it a moment for more people to hop on before we get started. Just for those who have just hopped on, we're waiting for a few more people, but while we're waiting, just a little bit of housekeeping. So on the bottom of your screen, there is a Q&A button. You can submit your questions on here anytime during the presentation, but we'll collate them to the very end to spark a conversation with our speaker. Questions are also open for all attendees to view, so we do encourage you to use the upvote function on any questions you're curious about too. This webinar is also being recorded today and will be shared in the very near future. We're at 12:01, so I will hand it over to Chris to get us started.
Kia ora, I'm Chris White. I'm one of your RTSA committee members based in Christchurch, New Zealand. Firstly, we want to thank you for coming along at lunchtime. We know how valuable your lunchtime is. RTSA are a trans-Tasman organisation for anyone with a professional interest in railways. We aim to provide technical topics of interest, support the business of the railway industry, support the continuing professional development of its members, and promote close working relationships amongst participants in the railway industry. We hold regular face-to-face CPD events, webinars, training and education, awards, a knowledge bank, conferences, study tours, and we're always open to hearing what events as members you would like to see available. We always welcome any new members, so if you're listening and wish to join, please go on the How to Join section of the website. So today's presentation is on the application of LiDAR and digital imagery to solve track compliance and asset configuration assessments. That will be presented by David Presley from Agonics. So David's going to undertake his presentation, showing us the various use cases for LiDAR in the modern railway. Over to you, Dave.
Thanks very much, Chris and Caitlin. Good morning, everyone. It's your lunchtime, but it's my breakfast. I'm calling from Melbourne. Thanks for inviting me to give this presentation on the application of LiDAR and digital imagery to solve track compliance and asset configuration assessments. It follows some work that our company has been delivering to organisations including KiwiRail and Australian Railways, and I'll be presenting the applications that we've deployed using LiDAR and imagery to solve compliance and infrastructure measurement questions. In preparing this, I was thinking back to when I started my career, and to give you an idea of my age, I graduated in 1990. That's me, obviously, on the left. And one of the big changes that I've seen in the industry is, of course, the introduction of PPE. This is myself standing outside a tugboat on the way to deliver some pipe to an oil field. And as you can see, absolutely no PPE in sight, even though this industry is probably even more dangerous than rail. So that's been a big change in my career, but so also has technology. When this photo was taken, GPS was just being introduced into commercial applications 35 years ago. And what I'm going to be talking about is really an extension of that technology leap that KiwiRail, Agonics and other railways have been a part of over the past decade. At the top, most of what I'm going to be talking about comes from what is known as an MLS technology, which stands for mobile laser scanning. So in a mobile laser scanning project, there are three core instruments, I suppose, that are used to capture data. There's a laser, also known as a LiDAR system. There's digital panoramic imagery, such as what you'd see on Street View or Google Maps. And then there is GPS and inertial positioning technology that is used ultimately to assign accurate coordinates to all of the laser point clouds and digital photos that are captured. Here's an example of that technology or an MLS system. You can see the GNSS or Global Navigation System, aka GPS antenna, 360-degree camera, a scanner, in this case it's a Regal scanner, and an inertial measurement unit. And actually the real brains in that system is actually the grey coloured IMU, because without it, none of the other instruments would be able to be integrated. And that's, yeah, it's often underappreciated. I suppose people sometimes get fixated on the camera or the GPS or the scanner, but it's really the inertial navigation unit that measures heave, pitch and roll as that system is pushed through a railway network or a road network, for instance. These systems can be deployed on locomotives, and this is one that was instrumented a month or two ago in Melbourne, but there have been numerous examples of where MLS technology has been installed on locomotives and high rails. KiwiRail has just commenced an MLS laser survey. And so this is that same instrumentation installed on a KiwiRail Canter truck that was mobilised back in June this year to capture data over the KiwiRail network. Whether these systems are installed on high rails or locomotives, the capture's done at normal speed, so 40 or 50 kilometres an hour is no trouble for the system to capture dense point cloud data from a high rail, similarly from a locomotive. Recently, I suppose, in the last 4 or 5 years, to my knowledge, there's been in the order of about 30,000 track kilometres recording using MLS systems. Often these are done on a network-wide scale. However, projects are using MLS to deliver pre-works and post-works surveys over smaller sections of track, 5, 10, 20 kilometres of track. And it allows them, I guess, to source at the beginning of their project information about the infrastructure, the terrain, and the assets that are on the ground before they step onto site. It creates a record of pre-works dilapidation study of the site so that everyone's got a common understanding about if any infrastructure was damaged or in a poor state of repair before the contract began, and so the contractor is not responsible for that damage. And then at the end of a work, the point clouds generated from an MLS capture can be used to build up a post-works documentation, including asset data and drawings. So that's a national and a New Zealand, I suppose, coverage, but MLS is used very widely overseas, North America and Europe as well, to underpin ETCS and PTC or positive train control signalling uplifts. I'll soon show some examples of this technology in software, but just as on a couple of slides. So MLS systems capture high resolution digital photos every 5-10 metres as the vehicle is driven along the track. Here's an example of some photography captured through Flinders Street in Melbourne. A data point cloud is captured together with that imagery. Point clouds, potentially, I suppose nearly everyone on the call has had some experience with LiDAR point clouds, but they exist initially as a monochrome or a black and white point feature data set where every point in that cloud, so to speak, has an accurate latitude and a longitude. When the red, green and blue colours are taken from the camera feed and propagated into the monochrome point cloud, then the points in the point cloud, of course, can take on a colour appearance. So this gives a much more real world, I suppose, view of that LiDAR point cloud. And then the imagery in the sky can be integrated with the point cloud as well. So this is really the finished product, if you like, of an MLS survey where we have a very rich data point cloud. Every point, and in view there would be upwards of 5 or 10 million points, because scanners these days capture at 1 million points a second. So you think about how long it would take you to travel through that 100 metres of track in view. multiply that by 1 million. That's the number of points that you're looking at. And then each of those points has a latitude and a longitude and an elevation. This is in Melbourne, so it's GDA, but in NZ it'll be NZTM. A similar view, just showing again the point cloud density, just approaching the Sydney Harbour Bridge. Sydney Trains capture this level of data every 6 months across their network. Metro Trains capture it every 1 to 2 years. And this is the third photo that I'll show, and this is, I think, Bluff River in the South Island KiwiRail network. So you can see each point has a coordinate, and because there are coordinates, we can take measurements inside that point cloud, very simply. So that's a bit of an introduction to MLS, but really, whilst a lot of people get value from just having an image database at their fingertips of their network, and we all know, I suppose, how often we use things like Street View for navigation or to look at shops or what have you. A lot of value add, for want of a better expression, can be taken from an MLS data set when it is applied to solve track compliance and measurement problems that otherwise would be solved using manual or more conventional methods that work. MLS, though, and the data sets just offer an alternative, sometimes more accurate, often faster, and definitely more auditable when compared to manual methods. So I'll be talking about a few of these applications of MLS over the next 20, 25 minutes. The first one is asset mapping and data reconciliation. So the purpose of an MLS survey is often to deliver an updated asset database to an organisation, be it KiwiRail, be it Sydney Trains, be it Australian Rail Track Corporation or Metro Trains. And this is required because often GIS and asset management systems just become out of date. People move around organisations, different depots or regions place a different focus or priority on maintaining their asset database. And occasionally customers switch from one asset system to another, from Ellipse to Maximo, from SAP to Oracle, or from one GIS to another, such as Esri. So at the moment, KiwiRail has embarked on this MLS survey to help build up its GIS and its Maximo asset database. The inputs, of course, are an MLS survey with client-specific asset schema, which assets are needed to be extracted from the point cloud. And then to help uplift the asset management system, an extract can be taken of the existing customer's asset system, shoehorned into the point cloud so that very quickly you can do a differencing exercise and output then an authoritative asset database and GIS database of the track infrastructure as it was at the time of the survey. I'll try and illustrate some of this now by switching. Okay, so hopefully now you're looking at a map that shows some LiDAR and some MLS coverage. If I switch back, sorry, just a second. What I'm going to do is I'm going to take a coordinate and paste it into this software. Now what this will do, this will zoom me into a part of the, I'm actually using some KiwiRail data to begin with in the first example. So I'm opening up the MLS data and you can see there's the 360-degree digital photo. This is the truck that was used to capture this data. And then, as I mentioned at the top, every 5 meters, a new photo was taken. And here we can see we're approaching a signal. So I can see here, if I zoom in, that the signal has a label, 7TIA. If I turn on the LiDAR point cloud, and now you'll see the points being rendered over that signal. And if I go into an asset mapping view, what I can do now, because this software has preloaded the asset capture forms that are needed for mapping a signal. If I place a pin under that KiwiRail signal. So now at the back end, a coordinate has been saved and the software is now prompting me to give information about that signal. And I will just type in here test. And I think the label was 7TIA. The mounting type is a mast. And orientation, I will just take a guess at this, and it's facing. Now, if I hit save on that, what this has done is it's saved that asset into a database that now exists with accurate NZTM coordinates and features such as signal label, signal facing direction that the client, in this case KiwiRail, has said is important for it. If I move on, just as another example, in this way, this is how a database can be built up. Here we have a set of points. So if I turn on my point cloud again, switch to an asset mapping window, KiwiRail turnout. So we'll place a pin there. And then up comes the asset form for that particular turnout. Now, we can map the blades, we can map the last long bearer, we can map the points mechanism, etc., etc. But this is how we can build up either a point or a line or a polygon on that turnout asset. So I'll just close this. Base code, comment, test, label, test, and I think from memory it will be a right-hand turnout, orientation, facing, save. So now a second asset has been saved. I should have done that as a point, but it's come through as a polygon. So that quickly shows you the asset mapping power, I suppose, of an MLS data set. Moving into a different part of the KiwiRail network, you can see where these features have already been mapped at scale. And in the next few months, KiwiRail will be receiving an uplifted asset database of points, turnouts, signals, IRJs, bridges, platforms, etc., based on a schema that's come from the Maximo asset management system. I'll switch back to the PowerPoint slide now. Ultimately, what this delivers then is a very accurate point line polygon database of track features, and the technique of capturing MLS and doing feature extractions being delivered to VLine and MTM and ARTC, amongst others, to help build up hundreds of thousands of accurate asset coordinates. A second application for MLS is to do large-scale clearance assessments where either existing kinematic envelopes and structure gauge envelopes are tested against the point cloud extents, or occasionally new rolling stock is the KEs are tested of new rolling stock, and also the point clouds can be used to verify if new infrastructure can be installed safely in close proximity to the track. Every railroad seems to have slightly different clearance standards, However, with the right inputs in terms of defining the kinematic expansion parameters, centre throw and end throw, bogey separation, and allowances for rail wear, etc., then the clearance templates can be accurately modelled within the LiDAR point cloud. This is an example for some work that's being currently undertaken by the Australian Rail Track Corporation in Australia, because this whole line basically between Brisbane and Melbourne is being modified so that it can take double stack containers. It's known as the Inland Rail Project. At the moment, this whole line, which runs for several thousand kilometres, is only designed to take single stack containers, but it's one of the major national rail initiatives in Australia to allow or support double stack container movements on track between Melbourne and Brisbane. As an example, this is typical of the type of report that a clearance assessment will generate. Each envelope can be tested independently, and the magnitude of that envelope where there is an encroachment can be automatically measured and output. As engineers, we love spreadsheets, so most things that an MLS survey delivers ends up as a spreadsheet report in one way, shape or another. But we can quickly carry the coordinates or the profiles of a particular incursion, which is what I'm going to copy in now. So if I go back to here and search for a profile. So this software will now fly to where that incursion was detected. And here we are here. So this is the map view. So if I recenter, this is actually in regional New South Wales. Just to zoom out and give everyone a sense of where we are. So we're sort of, there's Melbourne, there's Brisbane. So this is the inland rail route. If we zoom in here. The profile has landed us at this location. And if I play through, and if I generate a cross section where this signal gantry is, then hopefully everyone can see these are the outlines that have been preloaded into this particular track base code. So ARTC runs 3 plates through here, plate D, H and F2. F2 is the new double stack container outline. So you can see that there's been an incursion here. And in the report, what happens is that the measurement or the magnitude of that incursion against each buffer or each envelope is automatically detected through a point in polygon exercise. So customers can then triage, I suppose, which incursions are the most significant or which incursion may have been presented by a frangible piece of infrastructure, such as a sign or something else like that. So this is a very powerful application of an MLS point cloud. It allows us to generate cross sections or profiles at will across the network. And rather than having to only revisit known locations from, for example, a previous survey, this data allows us to basically run a whole of network incursion using multiple plates and a buffering system across literally hundreds or thousands of kilometres, just in a matter of hours, really. Customers have started to ask for reports to be basically built around using a buffer as well as the primary outline. So if the primary outline for F2 is this light blue shape here, then we can simply add a +100 or a +300 buffer to that outline so that we detect incursions that are within the buffer, but albeit outside of the primary plate. And this just helps railroads monitor, I suppose, changes to the network if that track happens to change location or if there's, for whatever reason, extra cant introduced. So that's an example of using a LiDAR point cloud for a network-wide clearance assessment. Go back to my slide deck now. Another application is to continuously monitor the track location in relation to known survey marks. Sydney Trains is a good example of this application of MLS data. Sydney Trains has a network of about 1,500 kilometres of track, and there are in the order of 22,000 TCMs, or track control marks or survey marks, that have been installed on their overhead wiring structures, portals, masts and gantries, and along some platforms and through some rock cuttings, primarily on track curves. Now, historically, Sydney Trains used to have to walk that track at least annually and measure using a tape or an offset bar what the lateral offset was from the outside rail to those survey marks, whereas this can now all be done relatively automatically using a LiDAR point cloud. And I'll try and show this. So this slide shows you where there is a TCM, or a known survey mark. That survey mark can be rendered as a classified feature in the LiDAR cross-section, and then there can be an automated process to measure from the near side rail out to that classified feature within that cross-section or within that profile. Oh, this is a typical report, once again, driven by Excel, that shows an alignment result through, this is just a short subset of a report actually, but it shows where the measured alignment from the point cloud, from the TCM to the near rail, differs from the design alignment. Now, this could be because the structure that the TCM on has leaned, perhaps, but more often than not, because these checks are done around curves, it's because the position of the track has slightly shifted just due to curvature and some expansion laterally. So this is a system to detect lateral creep, if you like. And I'll show an example of that. Once again, just taking a profile ID, which is really just a shortcut for me to search into the software. Do this. So now we're going to fly into a part of the Sydney Trains network. You'll notice in this case that the point cloud's just in monochrome. But if I show you in a photo, so here is where there is a survey mark on the face of the structure. There's a structure ID. Now that survey mark has a known lift and offset from the near rail that historically track workers would walk along and measure. But here we can see where the software has automatically detected that the actual distance is different to what was in design. So the software can measure from the point cloud gauge face out to where the structure is. The design measurement is 2.278, but that design measurement is actually now greater than what we will measure automatically from this cross-section view. So by using the LiDAR point cloud in this way, Sydney Trains are saving thousands and thousands of person hours each year by not having to walk the track. The TCMs, the beauty of the TCMs is by their very nature, they're tightly coordinated. So the point cloud can be inspected automatically by generating cross sections at known coordinates. The TCMs won't move. They may move slightly, of course, as relative to the track, as the track slightly shifts, but in an absolute sense, then that coordinate will be unchanged, which means that we can generate thousands of cross sections automatically from across the entire point cloud, and then automate the lateral measurement from near rail to the TCM. Go back to my slide. So that's three quick applications of MLS data. Another one that's come come through that I know railways are using point clouds to answer is signal sighting. So MTM completed an MLS survey about 4 years ago to build up an asset database for their new track inspection car. So KiwiRail is getting a new vehicle delivered by a company called Mermec. MTM went through a similar exercise 4 years ago and engaged a company from North America to deliver their car. That car needed a track database installed on it, so all of the gauge top line, cant and twist faults could be reported accurately with location information. As a byproduct of that, so that project was 4 years ago. 2 years ago, the signalling team at MTM realised that the LiDAR point cloud could also be used to assess signal sighting. The reason that was required was the new trains that MTM is bringing into their passenger fleet have a rather elongated nose cone, and the drivers' seat positions are further back and away from the windscreen. Now, for all intents and purposes, this means that the windscreen appears smaller, or the driver's field of view is slightly smaller. And so a driver sitting in the new train has a different view cone to that same driver sitting in all of the other MTM passenger trains. Now, as a car driver, we probably experience that changing view cone without really appreciating it. Although if you're trying to back a big four-wheel drive, you know you've got terrible sight lines. For train drivers, though, they need to be able to sight the signals at platforms where the train stops at a dedicated stopping line. And they also need to be able to sight mainline signals at a suitable time or distance, depending on line speed, away from that signal. So I'll now try and show how we're using an MLS point cloud to do a signal sighting assessment. This slide just illustrates the basic concepts. And once again, a report, and I'll talk about this at the end, that shows which signals are visible at which stopping distances. And sorry, I'll just go back to here, and then I'll grab a profile off here. So I'll go back to the software, go back to map view. So as I mentioned, this is I'll go to Metro Trains Melbourne, and we're in Flinders Street Station at the moment. So there we are. There's Flinders Street Station in Melbourne. I'll just turn that image off. This particular station has a signal at the end of the platform. And I will now go and show how we're doing this. I'll turn this. To help monitor or detect where the signal is, we've gone through and colorized the signal so that it stands out in relation to the black and white, if you like, point cloud. If I go to signal sighting, this is a signal at the stop line. So I can turn my windscreen on. Put my windscreen. So what we've done there is we've set, if I go backwards, sorry, go forwards now. Just ignore the shape on the right. That's where we've simulated another signal. But here you can see that if I set the software to place the driver at the stopping line, so he's 0 meters away from the stop line, then his driver view cone, or her driver view cone, sorry, will mean that the signal is not visible because the driver's field of view is only within these windscreen extents. So what Metro Trains have done here is they've said, well, if we step the train back 2 meters, 3 meters, 4 meters, 5 meters. So if the driver moves back 5 meters, or if the stopping line is moved back 5 meters, then suddenly that signal comes into view for the driver. The challenge here is that the new trains are a 7-car set. The current fleet is generally a 6-car set. The platforms are bi-directional and, of course, at a fixed length. So it's not always possible to simply move the stop line. Occasionally, MTM or the operator will need to put in a coactor, or they may actually need to lift the signal or completely relocate the signal. This is a system that's been used now to report hundreds of signal sightings at stop locations and through the main line for signals at speed. So, and the report that this system generates using the point cloud data then is reflected back in a spreadsheet such as this to show for the different driver head positions where that signal is visible or not visible. The head positions, if I change my driver head position to be top left head position, bottom left head position, a median head position, top right or bottom right, because there are allowable movements that the driver can take when they're in this position, and that the standards for signal sighting sort of compel. So that's an example of using a point cloud to do a signal sighting assessment. Platform reports are something that can be done automatically using MLS data. The railheads and the coping edge are automatically detected. And once again, spreadsheets can be generated automatically showing distances or changes along the platform. The door positions for different rolling stock can be superimposed on the platform, on the chart. And then the variation between the standard for horizontal and vertical offset and what the observed horizontal and vertical offset can be measured very easily, allowing railroads to then work out, well, has the track slewed, has a coping stone on the platform slipped, or why is there suddenly a change between the relative positions of the rail and the platform coping edge from one year to the next. For the MTM project that I spoke about a minute ago, the new trains, as well as having a different driver view cone, also have automatically deployed boarding ramps. So the LiDAR point cloud shows the surface of the platform to a great degree of detail. And what this company has been able to do is to use the kinematic outline of the new vehicle at a resting position on the platform, and then virtually deploy the boarding ramp down from the train step down onto the platform surface, and then simply calculate, well, what is that boarding ramp slope? And it needs to be more gentle than 1 in 8 to be compliant for disability accessibility. And so if the boarding ramp is deployed and it's steeper than 1 in 8, then MTM can pack the platform or put a small boarding ramp on that platform surface. Just 2 or 3 more quick examples. Tunnel investigation. So tunnel is obviously very hard to access, problematic to maintain. Melbourne has, probably count the number of tunnels on one hand, I think, but I know KiwiRail has upwards of 95 or 100 tunnels on the network. So having an accurate database of tunnel surfaces means that the data can be reused to do all sorts of investigations. Quickly show you a New Zealand tunnel. Just sorry. Oh, actually, bookmark. This is a tunnel on the South Island. I think we're just north of Christchurch. So once again, a 360-degree image through the data, playing through every 5 meters. Suddenly, there's now available a data set of this quality. There was a lighting system put on this KiwiRail canter so that we could get really good imagery through the tunnel. And then the point cloud, of course, comes in as well. So this is now the LiDAR point cloud through this network. If I wanted to, for instance, generate a cross-section and measure the width of that tunnel. Sorry, I just need to go up here. Sorry, it's just loading while I do this. So there's a cross-section. If I, for instance, was interested in the width of the tunnel or from here to here, then a measurement tool, because every point in that point cloud has an accurate coordinate, I can simply measure from there across to there, and suddenly I know that that's 3.941 meters. In tunnels, there's been a lot of work recently retrofitting services through tunnels. For example, to install leaky feeder cables. So a project in Western Australia completed recently was to retrofit leaky feeder cables through the Subiaco tunnels under Perth. And I'll quickly show an example of that. So if I go here, so PTA are installing a new, as I said, leaky feeder cable and stanchion through this tunnel, but they were aware that the tunnel already had very tight clearances. So they provided the contractor with a CAD model of the standoff bracket and a nominal height on the tunnel wall that bracket was to be located. And then they requested that a clearance report be prepared based on a nominal standoff bracket dimension and height. That report showed where the standoff bracket was going to be too close to the KE outline or inside the KE outline. And then software such as this can be used to alter the height and the location and even the angle of that standoff bracket so that the optimum clearance could be, the optimum location of that bracket could be identified through the tunnel, and then a longitudinal plot could be prepared showing the height of the standoff and the type of the standoff as a longitudinal chart, so that clearances could be maintained across the full installation. So that's an example of that. I'm slightly conscious of time. I'll just quickly show one or two other examples. Point clouds can be used to generate ballast compliance reports, such as here where a template's being given. The railheads are used as a datum point, and then over and under ballast can be detected very simply by generating cross sections. Overhead wire, the contact wires detected in an MLS survey, as well as the catenary, so height and stagger reports can be prepared. And then for new infrastructure outside of tunnels, such as signage, CAD files of new signs can be rendered inside the point cloud, and then the tools can be used to drive the viewer backwards and forwards so that they can verify signage sighting distances. So that's a bit of a wrap up on some of the applications for MLS data once it's been captured. Just my final slide, some key takeaways. On pretty much everything that I've spoken about in the last 40 minutes, the MLS survey that sponsored, or sorry, the project that sponsored that MLS survey, once it was completed, elsewhere across the organisation, new projects have popped up recognising that the point cloud could be used for their particular use case. Often an asset survey sponsors the initial MLS project, but then signal sighting or platform or ballast or overhead wire or retrofitting leaky feeders through tunnels are identified as value adds that can be taken and used to exploit the point cloud. To foster that take-up of MLS data through an organisation beyond the original project, it's important to have reliable accuracy and completeness reports so that people know the limitations, I suppose, of the data that they're hoping to use, and to be fully aware of that. Capturing MLS data through a railroad obviously requires track access, and that's often not easy. We have to sort of slot in amongst an existing busy timetable for passenger and freight services. So it's critical that customers and railroads help facilitate that track access. I've mentioned Excel several times. We know that ultimately the people that are going to be using the results of an MLS survey are probably coming off doing that work in an existing way, and it's almost always a requirement that the results from an MLS survey are shoehorned into a reporting template that already exists. This just helps customers compare different measurements across campaigns and epochs, but it also helps change in that the reports look the same. It's just that the source of the information is now coming from an MLS point cloud rather than from a manual inspection. And then down the bottom, historically, I think, regardless of where I've worked, data is, if it's engaged or commissioned by one team within an organisation, sometimes only that team or that department or that depot knows of the data, and the expression would be just leaves it in the top drawer and doesn't know to share it or can't share it or doesn't want to share it. Whereas a point cloud and using cloud services such as AWS or Azure and web services means that all of that data and information can now be democratized, and you can put controls on it to limit access or to limit functionality. But as I mentioned at the start, often just getting visibility of your network with high quality digital photos and a simple to use user interface means that there's demand and there's applications for this data beyond just the initial sponsoring project, particularly for organisations that have a large geographic footprint, such as national railway networks. Chris and Caitlin, I've sort of run out of breath, but if there's any time left or if there are questions, I'm more than happy to take questions. Thanks,
Dave. That was a good presentation. I've got just over 10 minutes, so I'll run through some of the questions. For asset mapping, are there any issues related to free text usage? So I think this is alluding to inconsistent descriptions.
Yes, there are enormous amount of issues if you allow free text. That's why I don't do any asset mapping, because as you could tell by my typing, I'm not very good at it. yeah, look, it's always better to use a schema that has preset valid options for features and attributes of an asset. Some customers actually want the text of trackside signage typed in, so you have to be careful when you're doing that. But most of the time, free text is avoided, and with either radio buttons, yes, nos, or pick lists, that's how the integrity, I suppose, of the attribute data is maintained. So yeah, good question.
Thanks, Dave. Another question here. Why is a 360-degree camera used on a locomotive that takes up roughly half the view?
Yeah, that's a good question. That the particular contractor that did that work only has 360-degree cameras. They don't have 180-degree cameras. So they just put what camera they had onto that particular deployment. Most of the network surveys that have been done in the last 4 or 5 years have utilised high rails. The exceptions being the electrified networks of Melbourne and Sydney, where the contractor hasn't been able to get a high rail under the wire during daytime. And so the systems have been installed on client locomotives. You don't really lose anything by having half of the 360 images taken up by the vehicle, and you can make the software so that it always lands you with an outwards facing perspective so that you're not looking back at the vehicle. If you had a 180-degree camera, then yes, you could deploy that without any trouble. This particular contractor, though, only had 360-degree cameras, and it was easier to leave everything turn on, rather than to switch off the rear lenses.
Thanks, Dave. Got another question on accuracy and point cloud density. So it's, hi Dave, thanks for the presentation. You mentioned very accurate. What are the parameters and what controls for accuracy are used to capture data? For KiwiRail structure gauge, clearance assessments, alignment, there are very tight requirements and the point cloud doesn't seem to be very dense. Is that done for the presentation? How are the rail edges or track centerline extracted?
Okay. The point cloud, so when the point clouds are captured, typically using time, okay? So when the vehicle is stationary, then the data is logged, the laser is being logged. When the systems are traveling through, for instance, a tunnel, and the way the LiDAR is captured is there's a laser and rotating mirrors. So as the vehicle moves along through a tunnel where something will be reflected back through the full 360-degree profile, then the rate of point cloud capture is about 1 million points per second. So when you take that down to the rail level, then you will basically be getting thousands of points per square metre at the rail level. And across the rail head, which is roughly 70 millimetres wide, there will be in the order of 20 or 30 LiDAR points across the rail head. So that's a summary of the point cloud data density. It's certainly been dense enough for Sydney Trains to run all of their track alignment and kinematic clearances through. Sydney Trains run 8 different KEs through their network, and for the past 3 years, annually, they've used LiDAR point clouds to validate all of their KE clearances across 8 KEs through 1,500 kilometres of track. So, and Metro Trains do the same, ARTC does the same. The accuracy of the point cloud, there's 2 ways to answer it. There's what is known as a relative accuracy. So when a user measures between 2 points in the point cloud, for instance, if I was to measure between the gauge points on the left-hand rail and the right-hand rail, then that measurement I would be able to do within about 3 to 5 millimetres. So if gauge is nominally 1060, then if it's tangent track, new rail, there's been no wear, etc., 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 then I'd be confident of being able to take a profile cross-section measurement of, let's say, between 1057 and 1062. So plus or minus 3 to 5 mil for a measurement within the point cloud. In an absolute sense, the way that that point cloud is registered with the imagery and with the map and with a railroad's kilometre post network, for instance, you can think of that as being absolute accuracy, and that comes down to the accuracy of the GPS or the GNSS, because there's different forms of GPS constellations. And that is typically between 50 and 100 mil in terms of an absolute latitude and a longitude. And the way that's verified is by going back into the field with a completely independent survey system, such as a real-time kinematic GPS receiver, taking shots on features that are identifiable on the ground and in the point cloud, such as a platform coping edge or a bollard or some bolts on the base of a mast at a level crossing, and coming up with very accurate NZTM, in this case, lats, longs and heights based on an RTK survey, and then comparing them to the lats, longs and heights that come from the LiDAR point cloud. And generally we find that in an absolute sense, those coordinates will agree to within 50 to 100 millimeters in XYZ. Technically, we actually have done this through MTM, V-Line, ARTC and half a dozen other railroads, and at a 2 sigma confidence level. So that means like 96% of all points, we're confident are within 120 millimeters of their real truthful lats, longs and heights as verified by an independent surveyor. That can be tightened up because if the client has external control, such as through a tunnel where there might be survey marks every 10, 20, 30 meters, then you can use that external control to further enhance the absolute accuracy of the point cloud. I'm happy to talk about that offline later on if you want to go deeper into that answer.
Thanks, Dave. Probably just time for one more. Just out of curiosity, how did you go from overseeing pipe delivery from the oil fields to data mapping for the railway?
Sorry, what was the first part of that question? Tight?
How did you go from overseeing pipe delivery in the oil fields to data mapping on the railway?
Oh, would it surprise you to know that there was a girl involved? So yes, I worked offshore for 4 or 5 years doing pipeline installations and oil rig relocations from one place to another offshore, and doing site surveys offshore. And I was living in Singapore at the time, and then I met my current wife over there. I was also getting a bit tired of living out of a suitcase for 4 or 5 years. And so we moved back to Australia in 1995, and that was just when GPS was becoming more commercially available after the first Gulf War. And it happened to coincide with when the electricity sector in Victoria was privatised, and all of the new retail franchisees of our formerly state-owned business, they needed their own digital asset database. And so they had to go and commission someone to go and coordinate all of their power lines, power poles, street lights. And GPS was the way to do it. So that's how I sort of fell into using GPS and working on land. And then my career just moved from electricity into rail about 15 years ago. Thanks for the question.
Thanks, Dave. I think that's all we've got time for. I just want to thank everyone again for dialing in. And thanks to you, Dave, for presenting.
No, thanks, Chris, and thanks, Caitlin, for the invitation.
Okay, we'll wrap it up there.
Okay.
Thanks a lot.
Thanks, bye.